Alright, so hi. Today we will be talking about the shell method, which is another way of finding volume. Okay, so some important things I want to bring out is when you're talking about the actual formulas and you're talking about the actual restrictions on how to uh, restrictions on the actual shape that we're making. Okay, you want to be actually looking for some actual methods to to show you, okay, this method I'm going to use this way and this other method I'm going to use this way. Okay, so I want to show you something real fast. And this is once again borrowed from Krista King over at integralcalc.com. This is a great little sheet she made that really helps out with the calculus. Okay, so basically we're going to find volume by cylindrical shells, and what we're going to do is we're going to rotate about the x-axis or y equals. Okay, all right, so when our formula is in y equals form, we're probably going to be rotating it. Now here's the thing though, is that I need to get the function into x equals something in terms of y. Okay, my radius will be in terms of y, my cylinder will look like this, and here's what the actual integral is going to look like. So I'll type this out so that we're ready to work with it. Okay, so first off we're going to get this in terms of x, so that we can actually work across. So x will equal y to the 1/2. Okay, and we will divide this by, well, it actually will be y divided by 2. Yeah, let's get rid of the 2. That makes it needlessly complicated at this point. We're just introducing the idea. So let me go back over here. Let's get rid of the 2 there. Okay, there we go. Should make our job a lot easier. Okay, so now what we're going to do is we're going to rotate about y equals 1. Alright, so first off, we're going to write out the integral. Okay, so volume will equal. Okay, so here's everything all set up. Alright, now this is the circumference, but this right here will be our radius. So this is our circumference right here. This will be our radius. Okay, this function in terms of y, which is this up here, this is g of y up here. Let me fix that, there we go. Okay, this will actually be the height of our cylinder, and once again this will be our thickness. Our dy will represent our thickness. Okay. Alright, so once you have this formula written down, the general formula, we'll start plugging in a little bit, but we have to kind of draw it out just so we have an idea of what's going on. Okay, so we draw our axis, get everything all set up. Okay, we'll mark out a 1 and a 1. Okay, so what I'm going to do is, normally we would just draw this, but we're going to have to represent it a little bit differently. So normally this would just be something that looks like this right here. I'm going to move it over just a scooch. There we go. Okay, so that it meets into the certain spots. Okay, now we are bounded by y equals 0, okay, which is going to be our line down here, okay, our horizontal line like this, and we're going to be bounded by this one right here. So here's what it's going to look like, our boundary line. And I'll move it over a little bit just so we can all see it a little bit better. Okay, so that's going to be our boundary line on the right side. Okay, now we're going to rotate about y equals 1, okay, which is going to be this line right here. Okay, so we're going to be doing a rotation that looks like that. Okay, so what's going to happen is that my figure is going to appear up here pretty much the same way of what I just did. So I'm going to mark out 2, okay, because the whole length is going to be that. Okay, It's not the best drawing in the world, but it will work nonetheless. Okay, and it's bounded at the top because we're not going to go any further than that. So it's a shape that looks like this. So if I actually draw it out, okay, so it's going to look something like this. It's going to be kind of like a hollowed out bowl shape, something you would make in Woods class, you know, that type of thing. So it's going to be looking like this. Okay, so first off, our circumference, our 2 pi is not going to change. However, our restrictions are, so the volume that we're going to be doing with respect to is going to be from 0 to 1. So when we actually start writing out our things, okay, so we're going to go up to 1, down from 0, okay? Alright, so our 2 pi is not going to change. Okay, however, our radius, okay, if you remember, our radius is going to be the curve right here, and we're going to give it in terms of y. This is going to be y to the 1/2. Okay, so that's our radius in terms of y. Excuse me. Alright, now our radius is actually going to be with respect to the actual line up here. Okay, we'll use this in a sec, but I just wanted to name that curve before we started going crazy with it. Okay, alright, so the height would be y. Okay. Alright, so whatever y is, we would take that away from 1. So the actual radius would be 1 minus y. Okay, so this right here would be parentheses 1 minus y. Okay, alright, so that would be the radius. So basically whatever this is, you're going to minus whatever the height is going to be. So it'd be 1 minus the height, which would be a good way to start working around it. And in this case, it's going to be whatever y is. Okay. Alright, so that's a good way to think about how to use the line about which you're rotating to actually come up with the radius a little bit faster. Okay, now that we have that, so we have the 2 pi and the radius, we now have our circumference all set. Now to get the rest of the volume, we need the actual height of the object. Now the height of the object, we're going to go this way. Okay, so wherever this is, okay, this length right here is going to be 1. Okay, and whatever this is, this will actually be the actual height, but it will be in terms of this function. So whenever I want to actually find the height of the actual function, I will take 1 and I will minus this actual function to actually get down to it. So I'll take 1 and actually minus it. Okay, so in other words, it's also going to be 1 minus y to the 1/2. Okay, something that looks like this. And then to represent our thickness, I would just have the dy right here. Okay. Alright, now to begin to start solving this, I'm going to put the 2 pi in front, because you always want to put your constant out front. And you put your integral sign. Now what I'm going to do is I'm going to actually factor this out. So this will be 1 minus y to the 1/2. Okay, minus y plus y to the 3/2. Okay, and then you would have your dy. Okay. Alright, now when we actually work on this, this will be 2 pi. Okay. And then we actually go ahead and start our integration. Our integration is going to go from left to right. Okay, we'll first have y in place of 1, and then we go minus, well, when we add 1 to this 3/2, when we add 2 over 2 to this 3/2, we get 3/2. Okay, so we're going to divide by 3/2, which turns into multiplying by 2/3. So I'll put that in parentheses. 2/3 times y to the 3/2. Okay, and then minus, and then this one is going to be 1/2 y to the second. So that's pretty simple. And that's going to be multiplied by it. Okay. All right, and then this one is going to be the trickiest one of all, because 3 halves plus 2, so that'd be 5 halves. So this would be 2/5 times y to the 5 halves, which is what this would be. Okay. All right, and we would go from 1 to 0 on it. Okay, now when I plug in 1, these are just basically all these are just going to turn into their respective fractions. Okay, and when I distribute the 2 pi, so this would be, well, I'm going to leave the 2 pi out. Okay, so 2 pi times 1 minus 2/3 minus 1/2 plus 2/5. Okay, now when I plug in 0, this turns into 0, this turns into 0, this turns into 0, this turns into 0, and then times by 2 pi. That gets you, that doesn't get you anywhere. All right, so we're just going to leave it at this because we just plugged into 1. Okay, so this is going to turn into 2 pi minus 4 pi thirds minus pi plus 4 pi fifths. Okay, and then I would get a common denominator of 15 and actually work this out. Okay, so this would turn into 7 pi 15ths. And the beautiful thing about this is that this is a very exact answer. It works fantastic. Now, if I did want to find with relation of rotating about the y-axis, I would use that form again from Krista King. Okay, so I would have about the y-axis or x equals, I would set it y equals the function in terms of x. Okay, I would get the radius in terms of x, and it would be a vertical cylinder looking like this. And then the formula is pretty much the same thing, except I have an x and an f of x and a d of x to represent everything. Okay, and just remember, you're thinking about the radius and how to actually find it, and you're thinking about the height and actually how to find that. So these are the 2 hardest parts to get. But once you get those, everything else just becomes a piece of cake. Okay? All right. All right, that's it for working with volumes, arc lengths, and surfaces, part 3, which is the shell method. I'll talk to you later.